In continuation from the previous lecture, in today's lecture, let us discuss how to represent a given switching equation in a canonical form. So the basic definition of a canonical form. First, let us discuss definition of a canonical form. It is conforming to a general rule. This rule says that each term in an any switching equation forming switching equation or contributing in a switching equation must contain all the variables. Contain all variables. If the canonical form representation of any switching equation we consider, there are two canonical forms of switching equation representation we have in digital fundamentals. The first one, it is the sum of products. In short, it is represented as SOP. And the second canonical form that we may make use is the product of sum terms. That is represented as PO. Yes. And basically, when you go for this canonical forms, of any switching equation, when we are representing, not used for the simplification process. So hence, canonical forms are not simplified versions of equations. Are not simplified switching equations. The canonical equations always represents the unsimplified equations. In order to understand what exactly the POS or SOP, let us take an example which is representing a switching equation which is a function of three variables A, B, C. So with these three variables, how a min term or how a max term will be represented, first we'll learn, and later how the canonical forms of the switching equations in POS form or in the SOP form we will be deriving. So if the three variables are considered as ABC, the possible values on these three variables as represented as 2 to the power of will be calculated as 2 to the power of 3 variables, which is equal to 8 different combinations. So hence all the 8 different variable values in binary, if it is represented as 000, 001, 010, 011, 100, 101, 110, 111. If the min terms representation of these three variables, when they are considered, the term, min term, how it will be represented, it is as follows. Whenever in the min term, any variable, its value is 0, it will be represented with the complement. So hence, A, B, C, all the three variables are 0, 0, 0, and all these variables have to be ANDed. So hence, a product term or a min term which is going to be represented in the min terms representation as A bar, B bar, C bar. The next combination of input variables value 0, 0, 1 will be represented as A bar, B bar, C, all these variables by ANDing. So the next one is A bar ANDed with B ANDed with C bar. The next min term is A bar ANDed with B bar, B and C. The next term is A ANDed with B bar ANDed with C bar. The next term is A ANDed with B bar ANDed with C. A ANDed with B ANDed with C bar. A ANDed with B ANDed with C. This is how we will be representing a minterm, and already we have discussed how the minterm will appear in a truth table. Its value always will be 1. So the representation designation for each minterm, how do we do? It is using a small letter m. Wherever A bar, B bar, C bar, it will be represented through the notation as M0, the subsequent minterm as M1, M2, M3, M4, M5, M6, M7. Similarly, the max terms representation, how do we do with the same three variables input? For which, in the max term, we know that whenever variable appears as it is, it gives in the truth table a value of 0. So therefore, here A bar, B bar, C bar, because in the truth table, when the minterm is considered, it has to give an output value true condition as 1. In the max term, it has to give a value of 0. Hence, when A, B, C, if it is complemented, its value will change to 1. So how do we get max term? Because it is an logical OR of all the variables, 3 variables A, B, C. So since it has to give an output value of 0 in the truth table, we can get that value as 0 by ORing the variables as it is. So hence the max term is A plus B plus C. When you look at here, A, the next max term, A, B plus C complement. C value, since it is 1, when it is complemented, its value will become 0. So that time output can be a 0 value completely. So the next one is A ORed with B bar ORed with C. A ORed with B bar ORed with C bar. A bar ORed with B ORed with C. A bar ORed with B ORed with C bar. The next term is A bar ORed with B bar ORed with C. And the last term is A bar ORed with B bar ORed with C bar. Then the general notation or the notation, you can say that it is designation, or you can say that it is a notation. For a max term, what will be used? It is using a capital M letter. We will be representing the max term. Since the first term is A plus B plus C, the notation that we'll be using to represent this max term is M0. The next one is M1, M2, M3, M4, M5, M6, M7. So these are the min terms and max terms representation we have to know before we go for the canonical form of any SOP equation or any POS equation. So with this basic knowledge, now let us see how an canonical form for given SOP equation. We will be, suppose any switching equation it is given. If that equation has to be converted into an standard canonical form of SOP equation, then what are the various steps we need to follow to convert an non-canonical form, this canonical form of SOP equation? It is the procedure that we are learning for the conversion of non-canonical equation, switching equation to SOP canonical equation. For which, let us see the process what we need to adopt. Suppose a given switching equation which is not in a standard SOP form. So in that case, identify the missing variables in each AND term, or you can say that it is a product term. Okay. Then in the next step, and the missing term and its complement with original AND term. That is, an example to illustrate this one is, suppose we have x, y, z as a function of switching equation, three variables function. If the first product term is x, z, here in this case, missing variable is y. So hence you can R with y and y bar ANDed with x and z. That is, whenever you are ORing y with its complement, its output will be 1. So it will give the same variable, which was same product term, even after adding with this missing variable also. The third step that we need to adopt is that expand the term by applying distributive law. So that distributive law will say that x z, y and y bar, when it has to be distributed, this common variable among these two variables. So x z, y, x z, y bar. So that is how a non-canonical SOP equation we can able to convert into an canonical SOP equation. Moving further, now let us discuss to convert an POS, non-canonical POS equation to an canonical POS expression. So canonical form for POS equation. Whenever a non-canonical POS expression which is given, What are the steps we need to make use to convert into an canonical POS equation, for which the process remains the same but with a slight modification. The very first step during the conversion process is that identify missing variable. Missing variable in R term. In each R term, because the equation when it is considered will have multiple R terms. In each R term, the missing variable has to be identified. Or the missing term, it may be term or terms, and its complement with original R term. Okay. That is, to illustrate this one, suppose we have a function of three variables which consists of x, y, z, and the sum term, it is x plus y bar. When it has to be converted into an canonical form, the missing term has to be identified. In the given expression, the missing term is z. This z and its complement has to be ANDed, and that has to be ORed with the given term. Here, when the term with its complement, when it is ANDed, always it gives a value of 0. So hence, after adding the term with the missing term and its variable, after ANDing, it gives the same result. So after ANDing, expand the terms using distributive law. This law states that x plus y bar plus z bar can be distributed amongst the variables as x plus y bar plus z as one term, multiplied this with another term as x plus y bar plus z bar. So this is how and given non-canonical form switching equation, if it is made with the product of some terms or sum of product terms, can be converted. In the next class, I'll be continuing with the K-maps. Thank you.